Welcome to the course on Introduction to Electrical Engineering. We will have a lecture 40 today on electrical measurement part 1. So, we starting from outline of presentation today, we will start with the introduction and classification of instruments, then electrical instrument, deflecting torque or deflecting torque and force, controlling torque or force and damping torque and force, and permanent moving coil instruments, then exercise and numerical valve followed by references. So, starting with the introduction, the measurement of a given quantity is essentially an act of the result of comparison between the quantity whose magnitude is unknown and the predefined quantity. So, there are two basic requirements of measurement, which are the standard used for a comparison and the apparatus used and method adopted. So, the method of measurement is the first category is the direct method. The unknown quantity is directly compared to the unknown quantity and result is expressed in numerical value and unit, and direct methods are quite common for measurement of physical quantity. It is also called absolute measurement. Well, the second approach of indirect is indirect method, and indirect method means that measuring something by measuring something else and more feasible and practicable than the direct method, and it is used in most of the engineering systems. It is more sensitive and more accurate than the direct method. And if you talk about the direct method here, we have here and measurement is performed using the scale of the measuring instrument, and the indirect method we have a comparison with the reference device, as it is shown the B is the reference device and A is the to be measured like. So, now coming to application of measuring instrumentation. So, every application typically of measurement include those not yet invented can be put in one of these three category of some combination of them, like a monitoring of process and operation, control of process and operation, and experimental engineering analysis. So, monitoring of processing and operations, the measuring device is being used to keep the track of some quantity. So, certain applications of measuring instruments may be characterized as having the essential a monitoring function, for example, thermometers, barometers and water, gas and electric meters, auto speedometers and fuel gauge and compass, and of course, control of process. One of the most important classes of measurement applications, sensors are used in feedback control system, and many measurement systems themselves use feedback principle and their operation, and sensors are used in feedback system and feedback systems are used in sensors. And to control any variable in feedback control system, it is first necessary to measure it. So, typical example here is every feedback control system has at least one measuring device as a vital component. As you can see here, we have to measure the output and give as a feedback to the input along with the your typically the input variables, and normally after this it is a error signal which go to controller, and control output go to as the actuating signal to the plant which is to be controlled. So, of course, here we have a measurement of the output which is used as a feedback in the control of this system. So, while coming to experimental engineering analysis, in solving engineering problems, two general methods are available, theoretical and experimental, and many problems require the application of both methods and theory, and experiments should be thought of as complementary each other. So, of course, the measurement in our daily life are many, like a measurement permeates every aspect of human life. So, few idea where measurement have an impact on our lives are electrical engineering, mechanical engineering, chemical engineering, signal conditioning and processing, biomedical engineering, biochemical engineering, automation in irrigation, medical instrumentation and robotics instrumentation. And typical example, if you look into here instruments used in automobile, you might have seen the speedometers as well as the other measurement in digital analog form, and instrument used in home like a voltmeter, then energy meter and ammeter. Well, you might have seen the instrument used in electrical laboratory like a voltmeter, multimeter, wattmeter, power quality analyzer, and then the CRO, cathode ray oscilloscope. Well, research laboratory have a setup, typical example setup which have several instruments connected to the setup, as you can see from one setup to another setup, and typically the calibration instrument as well as lot of instrumentation in research laboratory. And typically the here if we talk about what it has, like induction motor fault testing setup, FLIR E60 thermal camera, then digital meter, 3-phase power loss supply, direct online starter, digital tachometer, induction motor with bearing faults, and computer graphical user interface GUI. And typical example, analog oscilloscope, then the VU meter, representation of signal level in outdoor equipment, and display of UV meter. Then the tube testers, test condenser characteristic of vacuum tube used normally long back, and then transistor tester, which still we are using in testing the transistor in the laboratory. Then spectrum analyzer, display the frequency spectrum of the signal, which normally we want to analyze, as you can see the frequency spectrum in these CRO spectrum analyzers. Then the analog tachometers, which normally measure the speed, as well as digital tachometer, contact type and non-contact type, we have a both type. Then the piezo photometer measures radio frequency signal and the noise. Then the Megger, which measures the resistance of winding of a motor or generator and measures the earthing resistance, and normally use even the for grounding resistance measurement. Then the LCR meter measures the inductance, capacitance and resistance of a component. Then the ESR meter measures the equivalent series resistance of capacitors. Then the curve tracer and display results. Then the function generator. Then the steel scale and vernier caliper. Then the especially instrument used in mechanical engineering, level diameter gauge and radius gauge. Then measuring tape and depth micrometer. And the pressure in instrument used in chemical engineering, like a pressure gauge, infrared thermometer, non-contact type. Then typical load flow ultrasonic liquid flow meter and residential urban gas meter. And the physical property measurement. Then the especially medical equipment, especially spirometer to measure the patient blood pressure, ECG machine. Now coming to, so these are the some of the example you might have seen day to day life, as well as in electrical engineering we use a lot of instrument and we do the measurement. Now coming to the classification of these instrument, we classified into many ways. Instrument is a device for determining the value of magnitude of a quantity or variable, and the earliest scientific instruments use the same three essential elements are a detector, an intermediate transfer device, and indicator, record or storage. So typical example here, it is a elements of generalized measuring system is a functional element of instrument, like starting from measured medium, then it goes to the as a measured quantity to primary sensing element, then variable conversion element, then variable manipulation element, then data transmission element and data representation element, and following the observer. Like of course, you can store the data also and have a playback elements like. So, now coming to primary component of it, like a primary sensing element. So, this is the element that first receive the energy from the measured medium and produces an output depending upon the some way of the measured quantity, like measured, and the output is some physical variable, for example, displacement or voltage, and instrument always extracts some energy from the measured medium. So, good instruments are designed to minimize this loading effect. Now, coming to second element, which we call it like a variable conversion element. The output of the primary sensing element may be electrical signal or any form, it may be voltage, frequency or any other electrical parameter. So, for the instrument to perform the desired function, it may be necessary to convert this output to some other suitable form. And now coming to variable manipulation element, the function of this element is to manipulate the signal presented to it, preserving the original nature of the signal. And the element that follows the primary sensing element in any instrument or measurement system is called conditioning element. Now, coming to data transmission element, when the elements of a instrument are actually physically separated, it becomes necessary to transmit data from one to another, and the element that performs this function is called the data transmission element. Now, coming to data presentation element. So, information about the quantity under measurement has to be conveyed to the personal handling the instrument or the system for monitoring, control and analysis purpose, and function is done by this function is done by data presentation element. So, in case data is to be recorded like magnetic shape, high speed camera or TV equipment, cathode ray tube, CRT, printers or printer may be used. So, for control and analysis purpose, either purpose like a through microprocessor or maybe computer may be used for the purpose. So, now the history of development of instrument around in the three phases as measuring instrument. So, first is the mechanical instrument, then electrical instrument and electronics instrument. The typical example for mechanical instrument is starting from they are very reliable for static and like a barometer, like a weighing measurement machine. So, the disadvantage that they are unable to respond rapidly to measurement of dynamic and transient condition. So, now advantage is relatively cheaper in cost, more durable due to rugged construction, simple in design and easy to use, and no external power supply required for operation, and reliable and accurate for measurement of stable and time in a well quantity. Now, disadvantage are typically poor frequency response to transient and dynamic measurements, large force required to overcome mechanical friction, and incompatible when the remote indication or control needed, and cause noise pollution. So, now in electrical instruments, the measuring instruments that uses mechanical movement of electromagnetic meter to measure the voltage, current, power, etc. is called electrical measuring instrument. For example, an ammeter or permanent moving coil meter like. The advantage is non-contact measurement are possible, and these instruments consume less power, compact in size and more reliable in operation, and greater flexibility. Then remote indication and recording possible, and amplification produced greater than that produced in mechanical instrument. There is of course, the disadvantage is the frequency response is poor because of these instruments associated with the mechanical movement. Now, coming to electronics instrument, in electronics device the only movement involved is that of electrons, and these instruments have very fast response. The example, a cathode ray oscilloscope in short called CRO is capable to follow the dynamic and transient changes of the order of few nanoseconds, order of 10 to the power minus 9 seconds. Advantage, electrical or electronic signal can be amplified, filtered, multiplexed, sampled and measured, and many measurements can be carried out either simultaneously or in rapid succession. Electronics measurement makes possible to build analog or digital signal, and high sensitivity, low power consumption and a high degree of reliability are the important features of electronics instrument. Now, coming to electrical instrument, these instruments are classified into two categories, analog instrument and digital instrument. Analog instruments is the instrument that uses analog signal to display the magnitude of quantity under measurement. Typical example is here, as you can see the voltmeter, how the indication is there, then ammeter, then typically the many measurement associated with that. So, digital instrument uses digital signal to indicate the results of measurement in digital form. The typical example is here, how you see the digit here, or you can just see in multimeter the kind of digit, or you can have a speedometer with the digit like. Now, coming to analog instruments, these are also classified further in two categories, absolute instruments and secondary instruments. So, in absolute instrument, the measured value is given in terms of instrument constant and the deflection of one part of the instrument. An example, tangent galvanometer, relay current balance, as you can see the tangent galvanometer. In secondary instrument, the secondary instruments are so constructed that the quantity being measured can only be determined by the output indicated by the instrument, and these instruments are already calibrated as compared to the absolute instrument. And for example, these are like a ammeter, voltmeter. Now, coming to classification of secondary instruments as a indicating instrument, recording instrument and integrating instrument. So, here typically the indicating instrument is the magnitude of quantity being measured is obtained by deflection of the pointer on a scale, and output is indicated either in analog or digital form like ammeter, voltmeter and wattmeter, as you can see here. Both analog and digital meters are there. And the recording instrument, any instrument which makes the record in any recorded medium of quantity being measured in order to save information and use it in another time. For example, XY recorder and oscilloscope and recording instruments like. So, they comes as a recording instrument, or you can have like a integrating instrument. The total amount of either electricity or electrical energy supplied over a period of time is measured by these instruments. An example is ampere hour meters or watt hour meters or energy meters. So, it is all is measured like a kilowatt hour meter kilo kVh, which normally used in the your home for measuring the electricity quantity of electricity consumed by a house or premises like. So, analog coming to analog instruments may be classified according to the principle of operation they utilize, and the effect they utilize are magnetic effect, then heating effect, then electrostatic effect and electromagnetic effect, and then Hall effect. So, these are the like typically based on which the conversion these use the effect or physical phenomena. So, majority of analog instruments include the moving coil, moving iron or electrodynamic utilizing the magnetic effect. So, here it is a moving coil between the two magnets N S and provide the deflection according to the signal applied to this instrument. The another is like a moving iron. So, we have a moving piece of connected to spindle and fixed iron piece with the fixed coil like. So, the effect of the heat produced by a current in a conductor is also used in thermocouple and hot wire instrument. Electrostatic effect is used in electrostatic voltmeter, and electromagnetic induction effect is used in induction wattmeter and induction energy meter, and the flux meter is based on Hall effect measurement like. So, now coming to typically of this analog instrument, starting from effect like magnetic effect, we have ammeter, voltmeter, wattmeter, indicating meters, and heat effect we have ammeter, voltmeter, electrostatic we have a voltmeter, induction effect we have a AC ammeter, voltmeter, wattmeter, indicating meter, and a Hall effect we have flux meter, ammeter and pointing vector meter. Now, coming to typically operating torque in the typically in analog instruments. So, these three types of torque are needed for satisfactory operation of any indicating analog instrument. These are deflecting torque, controlling torque and then damping torque. Well, deflecting torque, starting with deflecting torque value is dependent upon the electrical signal to be measured, and the deflecting or operating force is required to move the pointer from 0 position, and this torque makes the pointer move away from the 0 position to the desired reading, and the deflecting system acts as a prime mover responsible for the deflection of the pointer. Now, coming to controlling torque or force, this torque is responsible to compensate the extra deflection made by the pointer due to deflection torque. Hence, the desired reading is indicated, and when the deflecting and controlling torque are equal in magnitude, then the movement will be definite position or equilibrium. So, for example, is a spiral springs or gravity control are used for this purpose, and the functions of controlling systems are to produce a torque equal to and opposite to the deflecting torque at finally steady state position of the pointer in order to make the deflection of the pointer for a particular magnitude of current. So, to bring the moving system back to its 0 position when the force causing the instrument to deflect is removed. Now, coming to spring control. So, this type of control, one is the spring control. So, here a spring usually of phosphorus bronze attached to the moving system and use indicating instrument for control purpose, and the two springs A and B, as you can see in the figure, are wound opposite direction. So, that when the moving system is deflected, one spring winds up while the other unwinds, and the controlling torque is due to combined torsions of the spring. And now, for flat spiral spring, the controlling torque developed is typically here, as you can see the figure with the different parameters as well as the flat spring. So, T c typically controlling torque T c equal to E b T cube upon 12 into theta in Newton meter, where T c is into K into theta, because it is proportional to deflection like theta, and the T d damping torque is K 1 into I. So, K is your E b T cube upon 12 L. So, E is the Young modulus of a spiral spring material in Newton meter square, and B is the width of a spring, T is the thickness of the spring, L is the length of a spring, theta is the angular deflection in radian, and K is the spring constant. And now, coming to spring controlling torque is directly proportional to the deflecting angle of the pointer. So, to reduce the deformity per unit length, number of turns should be increased to avoid the temperature variation, two springs are connected back to back. So, coming to the essential requirement of 4 instrument springs are, they should be non-magnetic because the magnetic field should not affect it, and they should also have a low resistance temperature coefficient because their values should not change, and they should have a small resistance and sufficient cross sectional area, and they should be proof from the mechanical fatigue, and the springs should be free from the mechanical stresses. So, coming the advantage of these are scale is uniform, the reading are taken very accurately, and the system needs not to be vertical position, it can be used in any position, and this control is mostly used when compared to gravity control. Now, disadvantage of course are the control torque is fixed and the performance is temperature dependent. It is simple, rigid, but costlier. Now, coming to gravity control, as you can see here how it is the weight is that is responsible for the gravity control. So, in gravity control instrument, a small weight is attached to the moving system in such a way that it produces or restoring or controlling torque when system is deflected, and when the system deflect through a angle theta. So, it comes T c equal to W sin theta into L, that is W L sin theta, or T c equal to K p sin theta, or where the K p is W L, where K p is this a constant like. And the gravity controlling torque is proportional to sine of angle of deflection of moving system, and the gravity controlling torque can be varied by simply adjusting the position of control weight upon the arm which it carries. Now, coming the type of advantage offers, it is simple and cheap method, not affected by temperature variation, it does not deteriorate with the time. Disadvantage are have uniform scale and thus reading becomes difficult, non-uniform scale and reading becomes difficult, it increases the weight of the system, and this instrument should be placed on only vertical direction because of the gravitational, and it is not suitable for use in portable instrument because of that reason. The difference between gravity and spring control, in gravity control adjustable a small weight is used which produces the controlling torque, and spring control two here springs are used which exert controlling torque. The controlling torque can be varied in gravity control, whereas the controlling torque is fixed in a spring, and in gravity the performance is not temperature dependent, while in the spring the performance is temperature dependent, and the scale is non-uniform in gravity, the scale is uniform in spring control. Well, the controlling torque is proportional to sine of the angle in the first, whereas then second the control torque is proportional to the angle. The reading cannot be taken accurately in the gravity, the reading can be taken very accurately in the spring. So, system must be used in vertical position only in gravity control, the system need not to necessarily in vertical position in spring control. So, power leveling is required as gravity control, the leveling is not required in the typically in your spring control. Now, coming to type of controlling system, let us see the effect of two type of control on shape of the scale. So, consider the instrument in which the deflecting torque is directly proportional to current being measured. So, T d is K d into I, where I is the current being measured, K d is the constant, K is the spiral constant, and theta is angle of deflection. So, at in equilibrium position the deflecting torque equal to the spring controlling torque, that is T c equal to T d, or K theta equal to K d I, or theta equal to K d upon K into I, or K 2 I, where the K 2 is K d upon K. So, therefore, the deflection is directly proportional to the current, the quantity being measured through the whole range of the scale in case of spring control. So, if the instrument is gravity control, then T c equal to K p into sin theta. For equilibrium position, T c equal to T d, or K p sin theta equal to K d I, or sin theta is K d upon K p into I, or K 2 dash I, and theta equal to sin inverse K 2 dash into I. So, suppose a current I max produces the deflection of 90 degree in both the cases, then the current I max by 2 will produce a deflection of 45 degree in the spring control instrument, and in gravity if gravity control is applied, we have sin 90 equal to K 2 I max. So, K 2 dash is your 1 upon I max, or I equal to I max by 2, and theta equal to sin inverse K 2 I dash, that is sin inverse 1 upon I max into I max by 2. So, theta comes sin inverse 0.5, that is 30 degree. So, thus while a current I max give a deflection of 90 degree, a current of I max 2 give a deflection of 30 degree. This means that the gravity control instrument does not give a uniform scale, and hence the gravity control taken on its merit give the cramped or compress or crowded scale at the lower end, and this is the disadvantage when the pointer lies at the lower scale value, and these will not be accurately read like. So, coming to like a damping torque or force which required in these your analog instrument, indicating instrument. So, a damping force generally work in opposite direction to the movement of the moving system, and this opposite movement of the damping force without any oscillation or very small oscillation brings the moving system to rest at the final deflection position quickly. And type of damping is the air friction damping, fluid friction damping, eddy current damping. The typical example of air friction damping is here. You have a piston in a chamber, air chamber, which of course will provide the your air friction damping, or you have a vane, typically which also opposes the air friction. And then eddy current damping, certainly the because of the kind of magnets, the eddy current are induced in the your kind of aluminum disc which is rotating like, and producing certainly the restoring torque like for providing the damping. So, coming to like a damping torque, we have a 3 condition like a under damped condition. So, response is oscillative, that it means TD is much greater than TC. The critically damped condition, when the response settles quickly without any oscillation and system is said to be critically damped, that is TD equal to TC. And the third is over damped, the response is sluggish and it rises slowly from its 0 position to final position, and TD is much less than the TC, and where TD is the deflecting torque and TC is the controlling torque. A typical example is here about the deflection of the pointer on the scale in all 3 conditions. So, A is the under damped, as you can see the oscillations there, it goes to over the final, typically the final position of head, and the second typical case is the B, that is the you can call it critical damp, and third is the C, that is the over damped. So, these are the how the deflection versus time is there. Finally, it had to be F, because that is the final position of indicating for a particular signal. Like now, coming to air friction damping, this air friction already we talk about, it has a typically a plunger piston air chamber. So, in this method a light aluminum piston is attached to the moving system and move in a air chamber close to one end, and the cross section of this chamber may be either circular or rectangular, and the clearance between the piston and the sides of chamber should be small and uniform. Now, coming to typically if the piston is moving rapidly into the chamber, the air in the closed space is compressed and the pressure opposes the motion of the piston and therefore, of the whole moving system. So, if the piston is moving out of the chamber rapidly, the pressure is closed space falls and the pressure on the open side of the piston is greater than that of the opposite side. So, motion is thus again opposed. Now, coming to second kind of damping, that we call it fluid friction damping. In this type of damping, a light vane attached to the spindle of the moving system dips into the pot of damping oil and should be completely submerged by the oil, as you can see here in the piston and the damping oil, and fluid typically related to fluid friction, and the friction drag in the disc is always in the direction of opposing motion, and there is no friction force when the disc is stationary. A number of vanes are attached to the spindle for providing the greater damping force, damping torque. The oil used must fulfill the following requirement: it should not evaporate it should not evaporate quickly, it should not have any corrosive effect on metals, and its viscosity should not change appreciable with the temperature. It should be good insulator. And advantage of course of fluid friction damping are the oil used for damping can also be used for insulation purpose in some form of instrument which are submerged in oil, and the clearance between the vanes and oil chamber is not a critical as with the air friction damping system, and the method is suitable for use with the instruments such as electrostatic type, where the movement is suspended rather than the pivoted, and due to the upthrust of oil, the load on bearing or suspension system is reduced, thereby reducing the frictional error. What are the disadvantages? Disadvantage: the instrument with this type of damping must be kept always in a vertical position, and it is difficult to keep the instrument clean due to leakage of wear, and it is not suitable for portable instrument. Now, coming to eddy current damping, which I also use in most of the cases. So, when the sheet of conducting material move in a magnetic field, so as to cut through the lines of force, eddy currents are set up as you can see in the figure. So, then a force exert between each currents and the magnetic field, which always in the direction of opposition to the motion according to Lenz's law. So, well, the force is proportional to the magnitude of current and the strength of the field, and the magnitude of the current is proportional to the velocity of movement of the conductor, and thus if the magnetic field is constant, the damping force is proportional to the velocity of the moving system and is 0 when there is no movement of the system typically in eddy current damping. Now, coming to support system, support system is typically for the in construction like a moving system should have the following property: the moving part should be light and friction force should be minimum, and support may be of the following type like suspension, taut suspension and pivot or javel bearing. So, typical example is how it is the taut suspension. You have a spring tension on both sides and you have a moving elements in between attached to the typically of this suspension ribbon, and or you have a typically simple suspension as you can have in case of like you have a upper suspension with meter and then you have a iron core stationary with followed by a moving coil and iron with the magnets on both the sides, or you have pivot and jewel bearing, the core taking the typically the movement of this with the core, coil and former. Now, coming to typically permanent moving coil instrument which are normally used in on the DC circuit, they are also used in of course in the rectifier along with the rectifier in case of the AC measurement, but primarily they are used for your DC measurement because permanent material is involved into that, like the other element of the or you the coil you can only produce the DC like. So, you have here the permanent instrument is the most accurate type of DC measurement. Now, you can see here we have a pivot and jewel bearing followed by spring balancing weight, and then we have a mirror and pointer with the scale, then you have a core as a coil former and you have pivot and jewel, so and with the permanent. So, here of course, this is the typically core with the coil former. So, in the coil only we have to just put the signal to be measured like. The principle on which the permanent moving coil instrument operates is that torque is exerted on a current carrying coil placed in the field of a permanent, and typically what permanent moving coil instruments consist of 5 main components. First is the moving coil. The moving coil can freely move between the two permanent magnets, and the coil is wound with many turns of copper wire and placed on a rectangular aluminum which is pivoted on javel bearing. We have a permanent, so highly intensity high coercive force magnet, and magnets are made of Alnico max or Alnico for higher coercive force and better field intensity. And we have a control system here. The control torque is provided by the two phosphor bronze hair springs, and this spring also serves lead current in and out of the coil. As you can see the spring and controlling here. Then the damping system, eddy current damping is used using aluminum former placed in the magnetic field and pointer scale. As you can see here, the meter of these instruments consist of lightweight pointer to have free movement and scale which is linear or uniform and varies with the angle. The weight of the instrument is normally counterbalanced by weight situated diametrically opposite, and you can have a internal structure of permanent moving coil which is all the part we have just talked about. We have a like a kind of permanent, then we have a moving coil, we have a spring on both the side, we have a pointer attached to this moving part, and as you can see like a hairpin and all that like. So, now coming to torque equation of permanent moving coil instrument. When the current flows through the coil, the force acting on both the side of the coil produces the deflecting torque, and consider the B is the flux density in Weber per meter square, L is the vertical length of the coil, L is the current flowing through the coil, and N is the number of turns of the coil. So, as Fleming left rule, the force acting on the coil due to the current flow is given by F equal to N B I L, and the deflecting torque T D is given as T D equal to force into perpendicular distance. So, T D will be N B I L into D, or you can say T D is N B I L D, and the area of the coil is A into equal to L into D. So, the total deflecting torque exerted on the coil will be T D equal to N B I in Newton meter. And now, for a permanent B is constant, flux density is constant, also for a given coil L, A and R constant, and thus product N B A is also constant, say K 1. Therefore, T D equal to K 1 into I. Now, coming to the control torque, the control of movement of the pointer over the scale is provided by two spiral wound phosphor bronze springs S 1 and S 2, at one at each end of the spindle S, and sometimes these springs are also conduct the current into an out coil, and the controlling torque of springs is proportional to the angle theta turned into the coil, that is T c equal to K s into theta. So, now T c is in K s theta. So, where the T c is the control torque and K s is the spring constant, and finally, steady state position control torque should be equal to deflecting torque. So, it means T c equal to D d or K s theta equal to K I. So, theta equal to K 1 upon K s into I, or K I, where K is K 1 upon K s like. So, the angular displacement of the pointer is directly proportional to the current. Thus, the scale of instrument is linear or uniformly divided in permanent moving coil instrument. Now, coming to sensitivity to small current, what are the advantages of permanent moving coil instrument? The permanent moving coil instrument consume less power and hence great accuracy and uniform scale up to 270 degree or more. The permanent moving coil instruments have a high torque to weight ratio, and it has a efficient damping characteristic and is not affected by the stereomagnetic field. It has a low power consumption and varies from 25 microwatt to 200 microwatt, and it can be modified as an ammeter or voltmeter with suitable resistance and easily adopted as multi-range instrument. Now, what are the disadvantages of permanent? This instrument can be obtained only in direct current measurement. The coil being very fine cannot withstand prolonged overloading. It is costlier. The aging of the instrument permanent and the control spring may introduce some errors, and the moving system is very delicate and can easily be damaged by the rough handling. Well, what are the measuring range of typically of permanent moving coil instruments? Like for as a DC ammeter instrument alone measures 0 to 5 microampere to 0 to 20 milliampere, with internal shunt up to 200 0 to 200 ampere, and with external shunt up to 0 to 500 ampere. Now, DC voltmeter instrument alone measure 0 to 30 or 0 to 100 millivolt, and with the series resistance up to 20,000 or 30,000 volt like. So, that is virtually you can call it the first quantity, typically the your galvanometer rating like. Now, coming to armature shunts, we are extending the used for the extending the ammeter range. The moving coil instrument has a coil wound with very fine wire. It can carry only few milliampere safely to give full scale deflection, and for measuring higher current, a low resistance is connected in parallel to the instrument before to bypass the major part of the current, and the low resistance connected in parallel with the coil is called shunt. Now, typical example is shown here. Here is your galvanometer or meter, and we have a shunt in parallel with the RSH resistance. So, you can find out this RSH for a particular current measurement like. So, resistance of shunt can be calculated using conventional circuit analysis. RSH is the shunt resistance in ohm, Rm is the coil resistance, Im equal to IFS full scale deflection current, and ISH is the shunt current in ampere, I is the current to be measured. The voltage drop across the shunt and the meter must be same as they are connected in parallel. So, I shunt equal to R shunt equal to Im into Rm. So, I equal to I shunt, where I equal to I shunt plus Im and I shunt equal to I minus Im. Now, from the previous equations we can say R shunt equal to Im upon Is into Rm, and RSH or ISH equal to Im upon I minus Im into Rm. So, the ratio of total current to the current in the meter is called multiplying power of the shunt. So, multiplying power is M equal to I upon Im, that is 1 plus Rm upon Rs, and or RSH equal to Rm upon M minus 1. Now, coming to case of voltage multiplier. For measuring higher voltage, a high resistance is connected in series with the instrument to limit the current in the coil to safe value, and this value of current should never exceed the current required to produce the full scale deflection, and the high resistance connected in series with the instrument is called a multiplier. Now, coming to extension range of this, the value of multiplier required to extend the voltage range is calculated as under. RSC is a multiplier resistance, RM is the multimeter resistance, IM equal to IFS equal to full scale deflection current, V the voltage across the meter for providing current IM, and voltage to be V the voltage to be measured. The voltage drop across the shunt and it must typically the connected in parallel. So, V equal to IM into RM, or capital V equal to IM plus RM plus RSC, RSC equal to V minus IM RSH upon IM, or V upon IM minus RM. So, now you can say now multiplying factor will be M equal to capital V upon small v, that is IM RM into RM plus RSC upon IM RM, or equal to 1 plus RSC upon RM, or RSC equal to M minus 1 into RM. So, now coming to sensitivity, the coil of instrument may require a small amount of current into the range of microampere for fully scale deflection. So, sensitivity is sometime expressed in ohms per volt. So, sensitivity of voltmeter is given as S equal to total voltmeter resistance in ohm divided by full scale reading in volts. So, RM upon V, that is 1 upon IFS ohms per volt, where IFS is the full scale deflection current. Now, coming to typically some of the theoretical problem. Define instrument defined as a device for determining the value or the magnitude of a quantity or variable. Classify instrument based on their function. The instrument based classified on their function as indicating instrument, integrating instrument, and recording instrument. Why calibration of instrument is important? The calibration of all instruments is important, since it affords the typically opportunity to check the instrument against a known standard or subsequently to error in accuracy. Now, name the different essential torque in indicating the instrument. Essential torque in indicating instruments are deflecting torque, controlling torque, and damping torque. Now, what are the palm magnet made of? Palm magnet made of special alloys such as aluminum, nickel, cobalt, and licoge, or strontium iron, or neodymium iron boron, or ceramic cobalt. What will happen if I use with the high frequency AC? If the frequency of AC is high, the meter vibrate in around the 0 value, preferably to verify with the center 0 meter, and finally stop responding to AC. How is the range of instrument can be extended in PMMC instrument? In ammeter by connecting a shunt resistor, in voltmeter by connecting a series resistor. How is the controlling torque provided in PMMC instruments? In PMMC instrument, controlling torque is provided by two phosphorus branch hairspring, either helical or spiral, coiled in opposite direction, normally equal in strength. What is the nature of the scale in palm magnet ammeter? The scale of palm magnet ammeter is palm magnet moving coil ammeter is linear. Deflecting torque of PMMC is proportional to current in the coil. So, what type of damping is used in palm magnet instrument? In palm magnet instrument, the damping torque is provided by eddy current damping, since the presence of palm magnet. Now, coming to some of the solved numerical problem. Starting from first numerical problem, the coil of a palm magnet instrument has 60 turns over a former is that 20 millimeter wide, and the effective length of the conductor being 25 millimeter. It moves a uniform field of flux density of 0.5 Tesla, and control spring constant is 1.5 into 10 power minus 6 Newton meter per degree. Calculate the current required to produce the deflection of 100 degree. So, total deflecting torque exerted on the coil is TD equal to NBI, and TD equal to, keeping value 0.5 into I 25 into 10 power minus 3 into 60 into 18 into 10 power minus 3. So, control torque of spring T c equal to K into theta. So, T c equal to 1.5 into 10 power minus 6 into 100. So, at equilibrium T d equal to D c. So, keeping a value, this T d and T c equal, we get a current, putting value we get 11.11 milliampere. Now, coming to example 2, a palm magnet moving coil instrument has a coil of dimension of 15 millimeter into 12 millimeter. The flux density in that gap is 1.8 into 10 power minus 3 Weber per meter square, and the spring constant is 0.14 into 10 power minus 6 Newton meter radian. Determine the number of turns required to produce an angular deflection of the 90 degree when the current of 5 milliampere flowing through the coil. So, total deflecting torque exerted on the coil is T d equal to NBI Newton meter, and T d then you can put the value here in terms of n, and the control torque spring is T c into Ks into 6, and T c you put the value that comes 0.14 into 10 power minus into 90.5 by 180, that equivalent T d equal to T c, and from here you can just find the n, putting the value of all that comes 136 tons. Now, coming to example 3, a permanent moving coil voltmeter with the resistance of 20 ohm give a full scale deflection of 120 degree when a potential difference of 100 millivolt is applied across it. The moving coil has a dimensions of 30 millimeter into 25 millimeter and is wound with 100 tons. The control spring constant is 0.375 into 10 power minus 6 Newton meter per degree. Find the flux density in the air gap. Find also the dimension of copper wire of the coil winding. If 30% of the instrument resistance is due to the coil winding, the specific resistance of copper density copper is 1.7 into 10 power minus 8 ohms meter. So, coming to as a full scale deflection current is I equal to 100 upon 20 into 10 power minus 3 ampere, as T d equal to N A B I in Newton meter. So, keeping a value in terms of B, so and control torque is equal to K T c equal to K to theta. So, that is given like a typically 120 degree. So, you can put the value and keeping a equal of both, then you get the B equal to 0.0112 Weber per meter square, and coil resistance come 20 into 0.3, that is typically 6 ohm. Now, if copper wire has a cross sectional area of a meter square, then N rho L upon A equal to R. Then N is the number of turns, rho is the resistive weight of the copper, L is the length of the wire, and A is the cross sectional area. So, putting the typical value here, we can get A value equal to 31.16 10 power minus 3 millimeter square. If D is the diameter of the copper wire, then we can find out the diameter of it, that is pi by 4 upon pi into typically A square, that comes equal to 0.199 millimeter. Coming to example 4, the coil of a moving coil voltmeter is 4 millimeter long and 30 millimeter wide and has 100 turns on it. The control spring exerts a torque of 240 into 10 power minus 6 Newton meter, where the deflection is 100 division on full scale. If the flux density of the magnetic field in the air gap is 1 Weber per meter square, estimate the resistance that must be put on in series with the coil to give the 1 volt per division, and resistance of the voltmeter coil may be neglected. So, let the full scale deflection current be I ampere. Total deflecting torque exerted on the coil will be T d equal to N B I. So, that putting a value T d in terms of like 1 into I into 4 T into 10 power minus 3 into 30 into 10 minus 3 into 200. So, we can call it control torque of a spring T c into K s into theta, and it means K into 240 into 10 power minus 3, keeping a at equilibrium T d equal to T c. So, you can get the value of I from here, it comes 0.002 ampere or 2 milliampere. If R is the shunt resistance, so R equal to V upon I. Putting the value, you get 50 into 10 power 3 ohms or 50 kilo ohm. Now, coming to question 5, a moving coil voltmeter has a resistance of 100 ohm. The scale is divided into 150 equal divisions. When the potential difference of 1 volt is applied to the terminal of the voltmeter, a deflection of 100 division is obtained. Explain how the instrument could be used for measuring up to 300 volt. Let the RSC be the multiplier resistance that will be connected in series with the voltmeter. So, voltage per division is 1 upon 100. So, voltage across the meter for producing the full scale deflection current V equal to 150 upon 1 upon 100, that is 1.5 volt. So, full scale meter reading meter current will be I m equal to 1.5 divided by 100 ampere, or you can call it, it comes like a typically 0.015 or 15 milliampere. So, meter resistance is R m equal to 100 ohm. So, R s c equal to V minus I m R m upon I m, that is V upon I m into minus R m. So, R s c comes like a 19.9 kilo ohm. Now, coming to example 6, a moving coil instrument has a resistance of 5 ohm and give a full scale deflection of 10 millivolt. So, how the instrument may be used to measure voltage up to 50 volt and current up to 10 ampere. So, full scale deflection is 10 millivolt and full scale deflection current is 10. Current is 10 into 10 power minus 3 divided by 5, 2 milliampere, and for measuring the voltage up to 50 volt, connect a multiplier resistance R s c in series with the instrument. So, R s c equal to m minus 1 into R m, where m is V upon V m. So, R s c equal to 50 upon 10 to power 10 into 10 power minus 3 minus 1 into 5, that comes 24,995 ohm or 24.995 kilo ohm. For measuring the current up to 10 ampere, connect the shunt in parallel to the instrument. So, R s is equal to Rm upon m minus 1, the m is I upon I m, that is 10 upon 2 into 10 power minus 3. So, it comes 5 into 10 power 3. So, R s is equal to 5 upon 5 into 10 minus 3 minus 1. So, it comes 1.002 into 10 power minus 3 ohm. So, it comes really 1 milli ohm resistance to be connected in parallel as a shunt. Now, coming to example 7, a moving coil ammeter has a fixed shunt of 0.02 ohm with a coil resistance of R equal to 1000 ohm and a potential difference of 500 millivolt across its. Full scale deflection is obtained to what shunt does it correspond to, and calculate the value of R to give a full scale deflection when shunt current I is 10 ampere, second 75 ampere, with what value of R 40% deflection obtained with I equal to 100 ampere. So, first A, current through the shunt ISH equal to 500 into 10 power minus 3 divided by 0.02, that is 25 ampere, and full deflection current is 10 into 10 power minus 3 divided by 5, 2 milliampere. The voltage across the shunt for a current of 10 is equal to 0.02 into 10, that is 0.2 volt. Therefore, resistance of meter for a current of 10 to give full scale deflection is 0.2 divided by 0.5 into 10 power minus 3, that is 400 ohms, and voltage across the shunt for the current of 75, that is 0.075 into 1, that is 1.5 volt. Therefore, resistance of meter of a current 75 to full scale deflection equal to 1.5 divided by 0.5 into 10 power minus 3, that is 30,000 ohm, and now 40% deflection is obtained with the 100 ampere. Therefore, the current to give full scale deflection is 100 upon 0.4, that is 250 ampere, and voltage across the shunt of 250 ampere equal to 0.02 into 250, that is 5 volt. Resistance of the meter of for a current of 100 ampere to give for a 100 volt full deflection, that is 5 divided by 0.5 into 10 power minus 3, that is 10 kilo ohm. Now, coming to example 8, a simple shunted ammeter using a basic meter movement with the internal resistance of 100 ohm and a full scale deflection current of 100 picoampere is connected in a circuit that gives the reading of 3.5 milliampere on its 5 milliampere scale. The reading is checked with the recently calibrated DC ammeter, which give a reading of 4.1 milliampere. The implication is that the ammeter has a faulted shunt on its 5 milliampere range. Calculate the actual value of faulty shunt and the current shunt for the 5 milliampere range. So, the 5 milliampere scale deflection correspond to 100 microampere. Therefore, 3.5 milliampere correspond to into 100 into 10 power minus 3 into 3.5 divided by 5, that is 7 into 10 power minus 5, or you can call it like a 70 microampere. As the shunt and the meter are connected in parallel, so drop across the shunt should be equal to the voltage across the meter. So, meter current is 7 into 10 power minus 5 ampere. So, shunt current is 4.1 into 10 power minus 3 minus 7 into 10 power minus 5 ampere. So, the actual value of the fault shunt is RSH into 4.1 into 10 power minus 3 minus 7 into 10 power minus 5. So, that comes 1800 into 7 into 10 power minus 5. So, RSH equal to 1800 into 7 into 10 power minus 5 divided by 4.1 into 10 power minus 3 minus 7 into 10 power minus 5. This comes 31.26 ohm, and 5 ampere scale deflection correspond to 100 microampere. Therefore, 4.1 correspond to putting a value, it comes 82 into 10 power minus 6 ampere. So, as the shunt and the meter are connected in parallel, then the drop across the shunt should be equal to meter drop across the meter. So, meter current is 82 into 10 power minus 6. So, shunt current is 4.1 into 10 power minus 3 minus 82 into 10 power 6 ampere. So, therefore, actual value of shunt fault shunt will be RSA equal to 4.1 into 10 power minus 3 minus 83 into 10 power minus 6. So, it comes 1800 into 82 into 10 power minus 6. So, RSH equal to 1800 into 82 into 10 power minus 3 divided by 4.1 into 10 power minus 3 minus 82 into 10 power minus, that comes RSH equal to 36.73 ohm. Now, coming to example 9, a moving coil instrument gives the full scale deflection of 10 milliampere when the potential difference across its terminal is 100 milliampere. Calculate the shunt resistance for full scale deflection corresponding to 100 ampere, and the B, the shunt series resistance for full scale reading with a 1000 volt. Calculate the power dissipation in each case. So, meter resistance Rm equal to 100 millivolt by 10 milliampere, that is 10 ohm, and shunt resistance corresponding to 100 ampere full scale deflection is R s equal to R m upon m minus 1. So, that is m equal to I upon I m. So, that is 100 upon 10 to power minus 10 upon divided by 10 into 10 minus 3, that is 10 into 10 power 3. So, I s is 10 upon 10 into 10 power 3 minus 1. So, that is 0.001 ohm, and R m, now R m and R s h are connected in parallel. So, equivalent resistance is R equal to R s h into R m upon R s h, and keeping a value it comes 0.00099, that is 0.99 milli ohm, and power dissipation P equal to I square R. So, keeping 100 square into that your 0.009 into that is 9.9 watt. So, resistance for the corresponding to 1000 voltmeter, that is R s equal to m minus 1 into R m, m equal to m capital V upon small v, that is your 1000 upon 10 to power 100 into 10 power minus 3, that is 10 to power 4. So, I s equal to 10 power minus 4 minus 1 into 10, that is 99,990 or 99.99 kilo ohm, and R s, R m and R s c are connected in series. So, equivalent resistance is R equal to R s h plus R m, that is your typically 100 kilo ohm, and power dissipation P square by R, so that is 10,000 square by your 100,000, that is 10 watt. So, now what will be the value of series resistance to be connected to external 0 to 200 volt range of your 20,000 ohms per watt voltmeter to 0 to 1000 volt. So, as the V s equal to V 2 minus V 1, that is 1800, and I s f d equal to 1 upon sensitivity, that is 1 upon 2000. So, V s equal to R s into I s, that is R s equal to 36 mega ohm, and there are solved problem which you can solve in the same way as we discussed about the solved problem, and these are the references from which we have created this material or developed this material, and thank you very much.